Hello, hello, sleepy soul, wherever you are right now, whether you are lying in a soft and darkened room or resting in a chair or letting your eyes grow heavy as the last light of the evening fades. Welcome. You are exactly where you need to be. There is nothing to do tonight, nothing to solve, nothing to finish. Whatever was left undone today, it will still be there tomorrow, patient and waiting, and you do not need to carry it into sleep with you. You can set it down. You can let it rest alongside you. And so can you. Tonight, we are going to travel somewhere very, very far away. We are going to visit a star. Not just any star. Not our small and steady sun, which rises and sets so faithfully that we have almost forgotten to be astonished by it. No, tonight we are going to visit the largest star that astronomers have ever measured. A star so immense, so slow, so ancient and enormous, that even the light moving across its surface takes hours to complete the journey. Its name is UY Scuti, and it has been burning for a very, very long time. Let your shoulders drop. Let your jaw soften. Let your hands relax wherever they lie. There are no sudden sounds in this video. No sharp cuts. No advertisements. Nothing will startle you. You are safe. And you are held, and the night is long, and there is no hurry at all. Simply listen, and let the universe tell you its story. To understand UY Scuti, we must first understand where it lives. Imagine, if you can, the Milky Way as seen from very far above, a slow, luminous spiral, like cream swirled lazily into dark coffee, turning so gradually that a single rotation takes over 200 million years. Within that spiral live hundreds of billions of stars. Most of them are small. Most of them are quiet. Most of them will burn for so long that the word forever feels almost accurate. But deep within one of those spiral arms, deep in the dense, dusty heart of the galactic disk, in a region so crowded with ancient stars that the night sky will look like a meadow of distant lanterns, there's such a constellation we call Scutum, the shield. Scutum is not one of the grand constellations. It does not sprawl across the sky like Orion or Sagittarius. It is modest, compact, easy to overlook, even on a clear night far from city lights. And yet, within its quiet boundaries, there burns something truly extraordinary. UY Scuti, a red hypergiant star, a sun so large that if it were placed at the center of our own solar system, its surface would extend beyond the orbit of Jupiter, perhaps even Saturn. We would not orbit it. We would be inside it. Tonight, across the next 2 hours or more, we are going to learn 36 remarkable and deeply calming facts about this magnificent star. We will move slowly through its discovery, its measurement, its color, its pulsations, its eventual end. There is no need to remember any of it. There is no test. There is only the gentle pleasure of knowing and the quiet companionship of wonder, and the stars drifting overhead as you close your eyes. Let us begin at the very beginning, with the moment a human I first noticed in the darkness that something extraordinary was there. In the year 1860, in the city of Bonn, Germany, a group of astronomers set themselves a quietly heroic task. Not a dramatic task. Not the kind of task that fills history books with bold ink and stirring quotations. Simply a slow, patient, methodical one. They were going to count the stars. Not all the stars, of course. That would be impossible. A number so vast it loses all meaning, the way a wave loses its shape when it finally meets the shore. But they were going to count all the stars they could see through their telescopes, zone by careful zone, declination by declination, moving across the sky with the same unhurried diligence that a cartographer might bring to mapping an unknown coast. Night after night, in the cool German air, these men leaned into their instruments and watched the sky. They noted positions. They estimated brightnesses. They recorded what they saw within, precise lines and thick, careful ledgers. The work was repetitive. The work was long. And the work was, in its own way, a form of reverence. It was during one of these unremarkable observing sessions, sometime in that year of 1860, that one of these astronomers noted a faint, reddish smudge of light in the direction of the constellation Scutum. A star, certainly. Nothing unusual at first glance. Just another point of light among the uncountable multitude, dutifully logged and passed over. They had no way of knowing what they had found. The technology of the time, the telescopes, the photographic plates just beginning to emerge, the measurements still dependent on the patient, fallible human eye, could not reveal the true scale of what sat behind that faint redness. The instruments were honest. They simply were not powerful enough to ask the right questions yet. And so the discovery was made and quietly set aside, registered, filed, forgotten in the way that extraordinary things so often are at first, before the world catches up with them. The star would wait. It was very good at waiting. It had, after all, been burning for millions of years before anyone looked at it at all. Sometimes the most important things are seen long before they are understood. The astronomers of Bonn looked at UY Scuti in 1860 and wrote down what they saw. They gave the universe something invaluable that night. Even if they didn't know it, they gave it a witness. Every star that was recorded during those long German observing sessions was given a name of a particular kind, not a poetic name, not a mythological name drawn from the old stories of gods and heroes and wandering monsters. Something more prosaic, more functional, the name of a file in a very large and very important cabinet. The catalog they were building was called the Bonner Durchmusterung. In German, this translates roughly to the Bonn Survey, a plain name for a plain but magnificent act. The systematic cataloging of over 300,000 stars visible from a northern and equatorial sky. The star we now call UY Scuti received the designation BD, 12 degree 5055. Let us sit with that name for a moment. BD stands simply for Bonner Durchmusterung. The 12 degrees refers to the zone of declination, the celestial equivalent of latitude, in which the star was found, in this case between 12 and 13 degrees south of the celestial equator. And the number 5055, that is simply its place in line, its position in the queue. It was the 5055th object recorded in that particular zone of sky. 5055. There's something quietly wonderful about that number. It means that before any astronomer's pen reached UY Scuti on that particular night, it already passed over 5,054 other stars in that same narrow band of sky. 5,054 points of light, each one a sun, each one surrounded perhaps by worlds we will never see, each one burning in its own way through its own long night. And then, number 5055, a faint reddish point. Noted, recorded, the pen moves on. The Bonner Durchmusterung was one of the great scientific achievements of the 19th century. It created a common language for talking about stars, a shared address system for the sky, and it remained a foundational reference for astronomers for well over a century. Some of its designations are still used today, preserved in databases and papers and quiet observatory notes, a thread of continuity running from an oil-lit study in 1860 to the humming servers of a modern space agency. BD 12 degree 5055, the 5055th star of the southern 12th declination zone. One day, it will be known as the largest star in the observable universe. But tonight in Bonn, it was simply next, to understand how the Bonner Durchmusterung worked, and why a star like UY Scuti ended up with the designation it did. It helps to imagine the sky as something that can be divided, ruled, made systematic. Astronomers have always needed ways to give directions in the sky. Much as we divide the surface of the Earth into lines of latitude and longitude, we divide the celestial sphere into coordinates. Right ascension moves like longitude around the sky. Declination, like latitude, moves up and down from the celestial South Pole at minus 90 degrees to the celestial North Pole at plus 90 degrees. The Bonner Durchmusterung organized its survey by moving through the sky in these zones. Each zone was a narrow band of declination, a thin horizontal stripe of the sky, just 1 degree wide. And within that stripe, every visible star was found and recorded from the starting point of right ascension all the way around the full 360 degrees of sky. UY Scuti fell into the zone between minus 12 and minus 13 degrees of declination. Imagine a very long corridor, a corridor that stretches all the way around the inside of an enormous dark room, following a single level, never rising or descending, just extending and extending until it meets itself. Along the walls of this corridor, stars are set like dim candles. Some are bright, some are barely visible. All of them are recorded, one by one, as the astronomer walks slowly forward. That is what a declination zone is. A corridor of sky. And within that particular corridor, the one that passes through the region of scutum, through the deep inner arm of the Milky Way, through the dust and brilliance of the galactic disk, there burn more than 5,000 individual stars, each one cataloged, each one given its number, each one a mystery the catalog had no room to solve. The astronomers moved methodically. They did not linger. They had too many corridors left to walk, too many zones left to survey, too many thousands of stars waiting patiently in their appointed places for humans to arrive with their notebooks and their careful eyes. And somewhere in the long walk of that 12th declination corridor, they passed a star that was, in fact, the largest object of its kind in the known universe. They kept walking. That, perhaps, is the most human thing about this story. Names are fascinating things. They begin as practical, a shorthand, a label, a way of pointing at something without using your whole arm. And then, slowly, they become something else. They become the thing itself. You forget that the name was ever arbitrary. The name becomes inseparable from what it names. For most of the time since its discovery in 1860, this star was simply BD, 12 degree 5055. That was its name. That was how it appeared in papers and tables, and the quiet internal conversations of astronomers who needed to refer to it, a functional designation, a postal address in the sky. But astronomy, like all sciences, continues. Instruments improve, methods refine, and over the decades following 1860, astronomers who returned their attention to this particular red point of light began to notice something it had been quietly doing all along. It was changing, not dramatically, not in a way visible to the naked eye, or even obvious through a modest telescope, but with careful measurement, patient observation over months and years, a pattern emerged. The star brightened and dimmed, not with the clockwork regularity of some variable stars, but with a more organic, more regular rhythm, as if something vast and slow was breathing. This made it a variable star. And variable stars, once recognized, enter a different naming system. The variable star naming convention, established over the 19th century and still in use today, assigns letter designations to variable stars within each constellation. The system begins with the letters R through Z for the first 9 variables discovered in a constellation, then moves to 2-letter pairs, RR, RS, RT, SS, SD, all the way through the alphabet, until, eventually, it reaches letters like Q, Z, and then begins again with a new format, UY. That is where this star fell in the sequence for the constellation Scutum. The 2 letters U and Y combined, a tiny piece of bureaucratic alphabet becoming, eventually, one of the most significant names in stellar astronomy. The prosaic BD designation did not disappear. It is still recorded, still used in certain contexts, a reminder where the star story began. But the name UY Scuti took hold. And now, when you say those 3 syllables, UY Scuti, they no longer sound like a postal code. They sound like something much larger. Something worth crossing the distance of 5,900 light years to see. There's a certain charm in learning that the naming of variable stars is governed by rules established in the 19th century and still follow today, more than 150 years later. Rules that were devised to handle, at most, a few hundred variable stars per constellation, and that have since been stretched ingeniously to accommodate thousands. The convention begins simply enough. The first variable star discovered in any given constellation is called R, followed by the constellation's name, our Scutum, our Leonis, our Corona Borealis. The next is S, then T, then U, then V, then W, then X, then Y, then Z. 9 variables, 9 letters, a reasonable system for an era when finding a variable star was still a relatively rare achievement. But what happens when there is a 10th? The system doubles back on itself with remarkable elegance. After Z, the designations begin again with 2 letter pairs: RR, RS, RT, RU, RV, RW, RX, RY, RZ, then SS, ST, SU, SV, and so on, moving through the alphabet with the patient industry of a committee that knows it will eventually need to handle a very large number of things. By the time you reach QZ, you have covered over 300 possible designations. And for the many thousands of variables discovered since then, the convention shifts to AV followed by a number: V335, V1500, V2491. But UY Scuti was found early enough to earn one of the old letter pair designations, U and Y. The combination places it in the original sequence as the 340th variable star listed for Scutum, which, given how star-rich the Scutum region of sky is, feels almost modest. Think about what that represents, though. 340 individual stars in one patch of sky, each one doing something dynamic, something worth watching, something that causes their light to change over time. Variable stars pulsate, or are eclipsed by companions, or shed their outer layers in slow exhalations. They are the dramatic ones, the restless ones, the stars that cannot quite keep still. And UY Scuti, the 340th variable of Scutum, turns out to be the largest of them all, not just the largest variable star in Scutum, the largest star yet measured anywhere. UY, a humble pair of letters, a simple convention, a name that turns out to carry, without knowing it, the weight of something almost unimaginably immense. What does it mean for a star to be variable? Most stars, for most of their lives, are extremely stable. Our own sun varies in brightness by less than 0.1% over its 11-year activity cycle. If you were watching it from another star system, you would not notice. You would see a steady, reliable yellow point of light, burning with the same quiet determination it has shown for the past 4.5 billion years. But some stars cannot hold still. Variable stars change. Their brightness rises and falls, sometimes over hours, sometimes over months, sometimes over years. The reasons are many. Some stars pulsate, their outer layers expanding and contracting in a slow, rhythmic cycle like a vast and luminous lung, breathing in and out over timescales we would never notice in a single lifetime, but that careful measurement reveals patient record by patient record. UY Scuti is a variable star of this pulsating kind. It varies in magnitude between approximately 7.9 and 10.6 on the stellar magnitude scale, a range that represents a significant change in brightness, easily detectable with the right instruments. Its period of variation is approximately 740 days, just over 2 years, though the pulsations are irregular and not perfectly predictable. Irregular. That word is important. There are variable stars that pulse like clockwork, so reliably that astronomers use them as distance measures across the universe. But UY Scuti's variability is more temperamental, more organic, more like the breathing of something truly alive than the ticking of a mechanism. Early observers who returned to the region of Scutum over weeks and months began to notice this quality. A star that was a certain brightness last week was slightly different this week. Not dramatically, not in a way that alarmed anyone, but measurably, consistently. The star was not the same from one observation to the next. That irregularity, that slow shifting of light, was the first real clue that something extraordinary was happening far out in the galactic disk. A very large star, in its very last and most restless phase of life, swelling and settling, expanding and relaxing on a time scale of years, under pressure forces almost too large to contemplate. Even in 1860, the star was already trying to tell them something. They were not quite ready to listen yet. Between our solar system and the heart of the Milky Way lies a great and beautiful obstacle. Dust, not the household dust of everyday life. The gentle gray accumulation that settles on shells and windowsills, made of skin cells and fabric fibers, and the ordinary detritus of living. This is interstellar dust. Tiny particles of carbon and silicates and ice, smaller than a human hair's width, drifting in the cold vastness between stars. Individually, each particle is insignificant. Together, gathered across thousands of light years of space, they form something remarkable. A veil. Astronomers call a region of sky near the galactic plane. The flat disk of the Milky Way is seen from our position within it. The zone of avoidance. The name is wonderfully evocative. It is a zone that early sky watchers avoided mapping, not out of superstition, but because it was so thick with dust and so bright with overlapping stars that it was nearly impossible to make out individual objects. The light from distant sources was absorbed, scattered, reddened by the dust between us and them. UY Scuti lies in this direction, roughly 5,900 light years away, in the direction of the galactic center, behind curtains of this obscuring dust. And yet, in 1860, the German astronomers found it. That is a testament to something simple and profound. UY Scuti is extraordinarily bright. Not bright in the way of our nearby neighbors. Not bright because it is close to us the way the full moon is bright, because it is only 250,000 miles away. Bright in the absolute sense. Bright in a way that allows its light to survive a journey of 6,000 years through dust and gas and the accumulated interference of the galactic disk, and still emerge on the other side legible to a human eye peering through a 19th century telescope. The dust reddens starlight as it passes through, because red wavelengths are less easily scattered than blue ones. This is the same reason our sunsets are red and orange. The light must travel through more atmosphere to reach us at the horizon, and the blue light scatters away, leaving only the warm tones. UY Scuti, already a red star by its own nature, would appear even redder to an observer on Earth, a double redness, the color of the star compounded by the color of its long journey home. The zone of avoidance tried to hide it, the darkness tried to swallow it, but UY Scuti burned through anyway, across 6,000 years of space, and landed, faint but real and indelible, on the retina of a night-adapted human eye in 19th century Germany. Something simply cannot be entirely hidden. Let us settle ourselves in the landscape. Let us take a moment to understand where, exactly, we are going when we visit UY Scuti. The constellation Scutum, the Shield, is a small constellation visible from much of the Earth, particularly prominent in summer skies of those in the northern hemisphere. It sits in the sky near the galactic plane, nestled between the constellations Aquila and Serpens, in a region of skies so thick with Milky Way stars that even a modest pair of binoculars reveals it to be extraordinarily rich. UY Scuti lies within Scutum at a distance of roughly 5,900 light-years from our solar system. In the context of everyday distances, even astronomical ones, this is not impossibly far. Alpha Centauri, our nearest stellar neighbor, is only 4 light-years away. The center of the Milky Way is about 26,000 light-years away. UY Scuti, at just under 6,000 light-years, sits somewhere between, in the inner galaxy, closer to the center than we are, in a richer and denser region of the galactic disk. A light-year, of course, is the distance light travels in 1 year, moving at the fastest speed the universe permits, approximately 186,000 miles every single second. In 1 year, at that speed, light covers roughly 6 trillion miles. 6,000 light-years, therefore, represents a distance of about 35 quadrillion miles, a number that, in the ordinary way, has no meaning, a number too large for intuition to grasp. And yet, it is not an infinite distance. It is a distance that light has already crossed. It crossed when UY Scuti's ancient photons began their journey, perhaps around the time our ancestors were first developing agriculture, first learning to write, first building the earliest cities in the river valleys of the ancient world. The light you would see from UY Scuti tonight, if you could see it with the naked eye, left its surface thousands of years ago and has been traveling ever since, 1 light-year per year, crossing the dark distances of the inner galaxy, threading through dust clouds, arriving finally, patiently, at the lens of a telescope that did not exist when the journey began. And as for what UY Scuti is, its type, its nature, it is a red supergiant, edging toward the category of red hypergiant. It is a star in the late stages of its life, burning to the last of its nuclear fuel with an extravagance born of desperation. It is vast. It is luminous. It is expanding slowly over centuries as it approaches the end of what will be a magnificently dramatic death. But we are getting ahead of ourselves. For now, Simply let the distance settle over you. 5,900 light years. A journey you could not make in a billion lifetimes, but that light makes without effort, year after year, patient as the universe itself. Stars speak a language of classification. Astronomers have spent over a century developing a system for describing the nature of a star from its light alone, from the pattern of wavelengths that its radiation contains, the specific fingerprint of atoms that absorbed or emitted that light on a long journey from the stellar surface to our detectors. This system, called spectral classification, reduces the infinite complexity of a star to a letter, sometimes a number, sometimes a few additional characters that carry the weight of immense physical meaning. UY Scuti spectral type is listed as M2 to M4, with a luminosity classification of IA to IAB. Sometimes it is described as an extreme red hypergiant. Let us unpack those letters gently, without urgency, the way you might unwrap something fragile and valuable. The letter M tells us this is a cool star. Cool by stellar standards, meaning that its surface temperature is somewhere between about 2,000 and 4,000 degrees Kelvin. Our own sun, by comparison, has a surface temperature of roughly 5,700 degrees. M stars are the reddest of the common spectral types. Their light dominated by long red wavelengths because their surfaces, relatively cool for stars, emit most strongly in that range. They are ancient-looking stars, ember-colored, the color of a coal that has been burning for a very, very long time and is beginning to show it. The numbers 2 to 4 within the M class tell us the temperature more precisely. M2 is hotter, still cool by stellar standards, but toward the warmer end of the M range. M4 is cooler. The fact that UY Scuti's classification spans this range is not a contradiction. It reflects the reality that the star is variable as it pulsates, as its outer layers swell and contract over those 740-day cycles. Its surface temperature shifts, and its spectral classification shifts with it. The Roman numerals that follow, IA and IAB, are the luminosity class. Class 1 stars are supergiants, the brightest and most massive stars in the sky. Class IA is the most luminous of the supergiants. Class IAB sits in between. The fact that UY Scuti is classified sometimes as IA and sometimes as IAB again reflects its variability. Its luminosity fluctuates along with its size, and the additional descriptor, the one that sometimes appears, extreme red hypergiant. This is not strictly part of the standard classification system. It is an annotation, a note in the margin of the catalog, saying, this one is different. This one exceeds the usual boundaries of what we call a supergiant. This one needs a new word, hypergiant, a word that astronomers use with care, because the universe has very few of them. Stars so extreme in their properties that the standard categories feel insufficient. Stars that burn so brilliantly, that swell so vastly, that they sit at the very edge of what physics permits a star to be. UY Scuti carries that word quietly, like a flag it has earned but rarely waves. There is a diagram that has been called, by those who love it, one of the most important and beautiful images in all of science, the Hertzsprung-Russell diagram, named for two astronomers, Ejner Hertzsprung of Denmark and Henry Norris Russell of America, who independently, in the early 20th century, noticed something profound. That stars are not scattered randomly when you plot their luminosity against their temperature. They arrange themselves. They cluster. They form patterns. Most stars fall along a broad diagonal band called the main sequence, stretching from hot, bright blue stars in the upper left corner of the diagram to cool, dim red stars in the lower right. Our sun sits comfortably, peacefully, about 2/3 of the way down this band. It has been there for 4.5 billion years. It will stay there for another 5 billion or so. The main sequence is where stars spend most of their lives. But at the upper right corner of the diagram, far from the main sequence, in a region that represents very cool temperatures combined with very high luminosities, there's a sparsely populated place, a zone that requires both qualities that rarely combine: the redness of an old, cool surface and the extraordinary brightness of a star that must be enormous to shine so powerfully despite that coolness. Because for a cool, red star be luminous, there is only one way to achieve it. It must be vast, almost incomprehensibly vast. Its surface area is so large that even the relatively modest output per square meter of a cool surface adds up across that immensity to a blazing total luminosity. That is where UY Scuti sits, nestled in the upper right corner of the Hertzsprung-Russell diagram, on the evolutionary tracks that correspond to stars beginning life with somewhere between 25 and 40 times the mass of our sun. The uncertainties in measurement are significant. More on this in later facts. But even accounting for those uncertainties, the position is unambiguous. UY Scuti is a hypergiant, one of the rarest and most extreme objects in the galaxy. There are perhaps a few dozen confirmed hypergiants in our portion of the Milky Way. In a galaxy of hundreds of billions of stars, a few dozen. They are not a population so much as a collection of exceptional individuals, each one burning with an intensity that its own physics can barely sustain, racing to the last phases of a stellar life that began in an explosion of gas and gravity millions of years ago. On the diagram, UY Scuti is a single faint red point in a lonely corner of the chart. On the diagram, it looks small. Everything on the diagram looks small. Let us speak very slowly about size, not in abstract terms, not in the language of mathematics alone, though the mathematics is there and it is staggering. Let us try, instead, to let the scale arrive gently, the way deep cold arrives on a winter night, not all at once, but gradually, settling into you until you feel it everywhere. UY Scuti is widely regarded as one of the largest known stars in the observable universe. That sentence deserves a pause. We know of hundreds of billions of stars in the Milky Way alone. We know of trillions of galaxies, each containing hundreds of billions more. Among all of those uncountable furnaces burning in the dark, UY Scuti is one of the very largest that has ever been measured. its radius is estimated in recent careful studies to be somewhere between 900 and 1,700 times the radius of our Sun. 900 to 1,700 solar radii. The range is wide because measuring the size of a star is genuinely difficult, and because UY Scuti's pulsations mean its size changes over time. But even at the lower end of that estimate, even if it is only 900 times the solar radius, the numbers are almost impossible to receive without a kind of quiet awe. Our Sun has a radius of approximately 696,000 kilometers. 900 times, that is over 600 million kilometers. The distance from the Earth to the Sun is approximately 150 million kilometers. So UY Scuti, at its smaller estimate, has a radius of 4 times the distance from our planet to our Sun. Stand on the Earth, look up at the sky, see the Sun, that small and brilliant disk, 150 million kilometers away. Now imagine that distance multiplied by 4, and that is merely the radius of the star, the distance from its center to its surface. If UY Scuti were placed at the center of our solar system, where our Sun currently sits, steady and warm and 4.5 billion years old, its surface would extend far beyond the orbit of Jupiter, past the asteroid belt, past Mars, past Earth and Venus and Mercury, past everything we have ever called our neighborhood. We would not be orbiting it. We would be inside it. Let that image rest behind your eyes for a moment in the soft dark. The solar system you have always lived in, the one with its 8 familiar planets, its rings and moons and drifting comets, entirely swallowed by a single star. And yet, from 5,900 light years away, it appears to us as a faint reddish smudge, a point too dim for the naked eye, something that required a telescope to notice in 1860 in a city in Germany. The universe does not shout. It contains its wonders quietly at enormous distances and waits for us to look carefully enough to find them. Numbers have a way of failing us when we need them most. We can say that UY Scuti has a diameter of approximately 2.4 billion kilometers. We can say that correctly. We can write it down and read it back and nod with understanding. And yet the number lands without weight, because 2.4 billion of anything is simply too large for the mind to receive as a felt reality. We hear the number and we place it in the category labeled very large, and we move on. The vastness does not touch us. So let us try something different. Let us try duration. Light moves at approximately 300,000 kilometers per second. That speed is the fastest anything in the universe can travel. At that speed, light crosses the diameter of our moon in about 11 milliseconds. A blink is faster. It crosses the diameter of our Sun in roughly 4.5 seconds. A slow breath. To cross the diameter of UY Scuti, light would need approximately 8 hours. 8 hours. While you sleep tonight, while you move through the quiet architecture of your rest, through the shallow hours and the deep ones, through whatever dreams come and go in the soft dark. Light, moving at the maximum speed the universe permits, would be crossing just a fraction of the star's diameter. You would wake in the morning and the journey would still be incomplete. There's another way to feel the scale. Volume. Stars are spheres, and the volume of a sphere grows very rapidly with radius, much faster than the radius itself grows. If you double the radius of a sphere, its volume increases eightfold. If you make the radius 10 times larger, the volume becomes 1,000 times larger. UY Scuti, at its estimated maximum, has a radius roughly 1,700 times that of the Sun. 1,700 cubed is approximately 4.9 billion. 5 billion suns, compressed into a single shape, would fit inside the volume of UY Scuti. 5 billion suns. Our solar system, the Earth, the Moon, the other planets, the asteroid belt, all of it exists because of a single one of those suns. One. And UY Scuti contains a space for 5 billion of them. VY Canis Majoris, often mentioned in the same breath as UY Scuti when the conversation turns to the largest known stars, has a radius of approximately 1,400 solar radii. It is enormous. It is one of the most extreme objects in the galaxy. And yet, UY Scuti at its upper estimates is measurably larger. Not dramatically so. These are close companions in the conversation about scale, but larger. 2.5 billion kilometers of diameter, 8 hours of light travel, 5 billion solar volumes, and yet, in the sky, a faint red smudge. The universe keeps its most remarkable secrets at very polite distances. UY Scuti does not sit alone at the summit of stellar enormity. It has company. Rare company, a small and extraordinary gathering of stars so vast that they occupy a category of their own at the outermost edge of what stellar physics allows. Let us visit them briefly and gently, the way you might glance at the other mountains from the peak of one, not to climb them tonight, but simply to acknowledge that the world is larger than any single summit. Stevenson 2-18. This star, located in the constellation Scutum, the same constellation as UY Scuti, at a distance of approximately 19,500 light-years, has been measured at somewhere between 1,500 and 2,150 solar radii. If the upper estimates are correct, it may be the largest known star of all, eclipsing even UY Scuti. But 19,000 light-years is a very long way, and the dust and gas between us and it make precise measurement extraordinarily difficult. The number carries a wide margin of uncertainty, which is the honest companion of all measurements made across such distances. An ML Cygni. In the constellation Cygnus, the Swan, one of the few constellations whose shape genuinely resembles what it names, lies in ML Cygni, at roughly 5,250 light-years, with an estimated radius of about 1,650 solar radii. Like UY Scuti, it is a red hypergiant, shedding mass through powerful stellar winds, surrounded by a complex circumstellar envelope of gas and dust. VY Canis Majoris, perhaps the most famous of the stellar giants, VY Canis Majoris has been the subject of extensive study and popular fascination for decades. At about 3,900 light-years in the constellation Canis Major, the Great Dog. It has an estimated radius of around 1,400 solar radii and a luminosity of roughly 270,000 times the Sun. It was once thought to be the largest known star. It remains among the most extreme. Whoa, G64. This one is different. WHG 64 does not live in our galaxy at all. It resides in a large Magellanic Cloud, a satellite galaxy of the Milky Way, at a distance of approximately 163,000 light years. Its estimated radius of around 1,500 solar radii makes it one of the largest stars in the local group of galaxies that we can measure at all across that incomprehensible gulf of intergalactic space. Is a testament to both its extraordinary brightness and the instruments we have built. And UY Scuti, 900 to 1,700 solar radii, 5,900 light years. A red supergiant edging toward hypergiant status in the quiet shield-shaped constellation discovered in 1860 by German astronomers who did not know what they had found. There is no definitive champion in this list. The measurements carry uncertainties. The stars themselves are variable, changing in size as they pulsate. The dust between us and them complicates every measurement. What we can say with certainty is that these stars, this small and extraordinary gathering, exist at the very limit of what nature permits. They are the answer to the question, how large can a star become? The answer, it seems, is larger than you imagined, larger than you can easily hold in the mind, larger than almost anything else in the universe, and still somehow just a faint smudge in the sky. Let the list settle over you like a slow tide. Stevenson 2 to 18, and ML Cygni, VY Canis Majoris, Whoa G64, UY Scuti, 5 enormous names, 5 almost unimaginable objects, 5 stars burning quietly, far away in the long night. Hold out your hand in the dark. Now imagine the warmth of a candle flame, not close enough to burn, just close enough to feel that warmth, that gentle radiation of heat, is a version of something that every star does, including UY Scuti. Stars radiate energy outward from their surfaces in all directions, across all wavelengths of light, because they are hot. The hotter they are, the more energy they pour into each square meter of their surface. The hotter they are, the bluer their light. UY Scuti is not hot. By stellar standards, it is remarkably, almost paradoxically cool. Its surface temperature sits at approximately 3,550 degrees Kelvin, roughly 3,270 degrees Celsius. This is about 3,000 degrees cooler than the surface of our own sun, which burns at around 5,700 Kelvin. 3,550 degrees sounds enormous, of course. In any earthly context, it is. The melting point of tungsten, the metal with the highest melting point of any element, is only about 3,400 degrees Celsius. UY Scuti's surface would melt tungsten. It would incinerate virtually any material we have ever worked with. And yet, in the context of stars, it is cool. It is cool enough that the surface glows not white or yellow or blue-white, but red, a deep, dim ember red, the color of something burning very slowly, very steadily, with an enormous reserve of fuel that it is consuming at a sedate and stately pace. That redness is not a sign of weakness. It is a sign of age, of scale, of a star that has evolved far beyond the vigorous hydrogen-burning days of its youth, expanded to monstrous proportions, and now burns at its surface with a particular dim glow of something that has become too enormous to maintain the fierce heat of a younger, more compact star. And here is the extraordinary thing about that cool red surface. Despite the relatively modest temperature, despite the fact that each square meter of UY Scuti's surface shines with far less intensity than a square meter of our sun, UY Scuti is 124,000 to 340,000 times more luminous than the sun overall. The reason is pure geometry, surface area. When a sphere grows enormously in radius, its surface area grows enormously too, as the square of the radius. UY Scuti's surface area is so many millions of times greater than the sun's that even the modest energy output per square meter multiplies into a total luminosity that is nearly incomprehensible. Each square meter of UY Scuti shines more dimly than the same area of the sun. But there are so many more square meters that the total light output dwarfs our star completely. 3,550 degrees. A cool red ember, vast beyond imagination, pouring light into the galaxy at 250,000 solar luminosities. The universe rewards scale with brightness. Even when the flame burns low, there is a quiet irony at the heart of the largest stars. The smaller a star is, the longer it lives. Our sun, a modest yellow dwarf of average mass and average brightness, will burn steadily for approximately 10 billion years, a span of time so large that the 4.5 billion years it has already existed feels like only the beginning. Some red dwarf stars, smaller, dimmer, cooler, will burn for trillions of years, so long that the universe as we know it at its current age of 13.8 billion years is barely a prologue to their lives. But the massive stars, the hypergiants, the supergiants, the brilliant blue and white behemoths, burn fast and brief. The more massive a star, the more intensely gravity compresses its core, the more ferociously it fuses hydrogen into helium and helium into heavier elements, and the faster it exhausts its fuel. UY Scuti is believed to be somewhere between 5 and 9 million years old. On a cosmic timescale, this is very young. Our solar system is 4.5 billion years old. The Milky Way is over 12 billion years old. UY Scuti's entire life represents a fraction of percent of the age of the universe. A brief, brilliant flare compared to the long, slow burning of more modest stars. And it is likely near the end of that brief life. The enormous outer layers of UY Scuti are held to the star only loosely. Its surface gravity, despite the star's extraordinary mass, is extremely weak because the radius is so enormous that any point on the surface is incredibly far from the dense core that generates the gravitational pull. Stellar winds, driven by the intense radiation pressure of the luminous interior, strip material away from the outer layers constantly. This stripping is not gentle. It is not a light breeze lifting leaves from a garden path. It is a continuous, powerful outflow of gas and plasma, bleeding away from the star at speeds of hundreds of kilometers per second, carrying the substance of UY Scuti outward into the space around it, thinning the star even as it continues to expand. A star cannot lose mass indefinitely. It cannot expand indefinitely. At some point, perhaps in 100,000 years, perhaps in 1,000,000, a duration that is both cosmically brief and humanly incomprehensible, UY Scuti will reach the end, and when it does, it will not fade quietly. Stars of this mass do not retire. They explode. But that ending is still far away, measuring the only units that matter for a star: slow time, deep time, the patient arithmetic of nuclear fire. For now, UY Scuti burns. It sheds its outer layers like a slow tide. It pulsates. It glows red in the deep sky of scutum, 5,900 light years away, and it is in no hurry. Some things burn brightly and briefly, and that, too, is a form of grace. Around UY Scuti, there is a cloud. Not a cloud like the ones that drift across our sky on autumn afternoons, white and temporary and belonging in their way to the familiar world of weather and water. This is something different, something larger, something slow. UY Scuti is surrounded by an enormous envelope of gas and dust, extending outward from the star to a distance of approximately 400 astronomical units. One astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometers. 400 astronomical units, therefore, is about 60 billion kilometers in every direction from the star center. This cloud is the star's own substance, shed over millions of years of mass loss. The stellar winds that constantly stream away from UY Scuti's loosely held outer atmosphere carry gas and dust outward into surrounding space. Some of it drifts far. Some condenses closer in, where temperatures and pressures allow tiny solid particles to form, grains of silicate mineral, whiskers of carbon, flecks of iron and magnesium oxide, all infinitesimally small and impossibly numerous, gathering into the vast shroud that surrounds the star. This envelope is part of why UY Scuti is so difficult to measure precisely. The dust is not transparent. It absorbs and scatters the light from the star, reddening and dimming what reaches us. The star we observe from Earth is not quite the star that exists. Between us and its true surface lies this veil, ancient, expanding slowly, carried with the elemental material that will one day, when the star eventually ends, be scattered into space and perhaps, given enough time and gravity and chemistry, become part of something new. The dust envelope is not inert. It is a complex chemical environment. In the cooling outflow of gas, molecules form. Compounds that would not exist in the fierce heat of the stellar interior are stable here, in the outer reaches of the cloud where temperatures have dropped enough to allow chemistry to occur. The rate of mass loss that creates this envelope is staggering. UY Scuti loses approximately 5.8 times 10 to the -5 solar masses per year. Written plainly, each year it sheds roughly 1/18,000th of a solar mass. This sounds small until you remember that a solar mass is approximately 2 times 10 to the power of 30 kilograms, 2 followed by 30 zeros. The material loss from UY Scuti each year amounts to something in the order of 100 septillion kilograms. Gone into the cloud, into the slow drift outward for 100 astronomical units and expanding in the far future. This material will be the raw substance of something else. It does not know this yet. It simply drifts. In the cold outer reaches of UY Scuti's vast circumstellar envelope, something strange and beautiful happens. As the shed material from the star moves outward, cooling as it goes, certain molecules begin to form in the darkness. Water molecules, silicon monoxide molecules, hydroxyl molecules. The combination of a single hydrogen atom and a single oxygen atom, one of the simplest chemical bonds in the universe, and also one of the most common, under the right conditions. Conditions that the circumstellar envelope of UY Scuti provides. These molecules can be stimulated by radiation from the central star to emit light in a very particular way, not the broad, warm, diffuse glow of thermal radiation. Something more focused, something amplified. These are masers. The word stands for microwave amplification by stimulated emission of radiation, the microwave equivalent of a laser. In a maser, molecules are excited to a higher energy state by incoming radiation, and then, when they return to their lower state, they emit a precise, narrow beam of microwave radiation at a specific frequency. The emission is coherent, all the waves aligned, all traveling together, and this coherence makes it enormously bright and precise. Water masers, silicon monoxide masers, hydroxyl masers. All 3 types have been detected in the circumstellar envelope of UY Scuti. Each one is a fingerprint. Each one tells astronomers something specific about the molecule that produced it, its abundance, its velocity, its location within the cloud. By listening to these faint microwave signals from 5,900 light years away, astronomers can map the structure of the envelope, trace the flow of material, and understand the complex chemistry taking place in the cold dark around this enormous star. There is something deeply affecting about this. The star is shedding its own substance into space, a slow, continuous bleeding of material. And that material, in the process of drifting away, assembles itself into molecules and then sings, emits precisely tuned microwave light, calls out across the void with signals specific enough that we can identify not just the presence of water, but the particular way the water molecules are moving, their temperature, their distance from the center. The universe communicates in frequencies we had to invent instruments to hear. But once you have the instruments, The information is extraordinary. UY Scuti's envelope is not silent. It is singing quietly in wavelengths our eyes cannot see. And somewhere, pointed patiently at that portion of sky, a radio telescope is listening. Let us return to something we touched earlier and sit with it more fully. UY Scuti breathes, not in the way a lung breathes, not with the quick, shallow rhythm of a sleeping animal, not with the urgency of a body that needs oxygen to survive every few seconds. It breathes on a timescale of years. Its outer layers expand and contract in a cycle that takes approximately 740 days, just over 2 years, to complete. This makes it what astronomers classify as a semi-regular variable star of subtype SRC. The SRC designation applies specifically to late-type supergiants and hypergiants, cool, enormous stars that show this kind of pulsational variability. Semi-regular means a cycle is not perfectly periodic. It does not tick like a clock. It breathes more like a living thing, with variations in period and amplitude, sometimes shallower, sometimes deeper, never quite the same twice. During the expansion phase, the outer atmosphere of UY Scuti swells outward. The star grows larger. Its surface moves slightly farther from the center. And because the surface is spreading over a greater area, it cools slightly and the star's color reddens a little more. The brightness changes too, though not in the simple direction you might expect. The relationship between size, temperature, and luminosity in these enormous variable stars is complex, and the brightness does not simply increase when the star expands. During contraction phase, the outer layers fall back inward, the radius decreases, the surface warms slightly. The color shifts very gently towards something less deeply red. 740 days. While you have been asleep over the last 2 years, UY Scuti has completed approximately 1 full breath. The outer layers of the star 1,700 times the radius of the sun have moved outward and then returned. Billions of kilometers of stellar atmosphere, moving in slow orchestrated waves driven by the physics of radiation, pressure, and gravity, completing one single cycle. There is no way to see this change in real time, no way to watch it happen over the course of a night or a week. It requires years of measurement, patient records, the accumulated observations of many astronomers across many observing seasons to reveal the pattern, but it is there, slow, enormous, regular enough to be named, irregular enough to remain surprising. UY Scuti breathing in the dark of the inner galaxy, 2 years per breath, and we 5,900 light years away, watching its chest rise and fall. There is something quietly remarkable about the fact that you can see UY Scuti, not with the naked eye. The star is too faint, and the dust between us and it is too thick for unaided human vision to pick it out. On a clear, dark night, far from city lights, the human eye can detect stars down to about magnitude 6. UY Scuti varies between magnitude 8.29 and 10.56, firmly below the threshold of direct vision. but with a modest telescope. It is within reach. Backyard astronomers with instruments of 100 millimeters or more in aperture, under reasonably good conditions, can locate UY Scuti in the constellation Scutum. It will not look impressive. It will look like a faint, slightly reddish point among many other faint points. You will need a good star chart to be certain you are looking at the right one. You will need to know where to look, and you will need patience, and you will need to give your eyes time to adapt fully to the darkness. But it is there, a real locatable point in a real observable patch of sky. And if you find it, if you center it in your eyepiece and hold it there, breathing quietly in the cool night air, you'll be looking at an object whose diameter is greater than the orbit of Jupiter. You will be looking at something so large that the light now entering your eye left its surface when humans were still in the early stages of recorded history. You will be looking at one of the most extreme objects in the observable universe, and will appear to you as a faint, unremarkable, slightly warm-colored. This is the universe's favorite trick. It hides its most extraordinary things in the guise of the ordinary. A mole on the back of your hand might be made of atoms that were forged in the core of a star that exploded long before the Earth existed. The breeze on your face is the same material, in a different form, that fills the space between galaxies. And a faint reddish that in the constellation Scutum is one of the largest objects in the observable universe. Magnitude 8.29 to 10.56. Fluctuating over 740 days. Slightly red, because it is an M-type star glowing at 3,550 degrees. Slightly dimmed, because the zone of avoidance does redden its journey to your eye. It is there right now, in the sky above you, behind the ceiling, behind the atmosphere, behind the daylight, or behind the nighttime clouds, or shining clearly in a dark autumn sky if the conditions are right. One of the largest stars in the universe, waiting patiently to be seen. How do you measure the size of something you cannot visit? How do you determine the width of an object 5,900 light years away? A distance so enormous that even at the speed of light, traveling without pause, it would take 6,000 years to cross. With enough precision to compare it to the widths of other distant stars and declare, with reasonable confidence, that it is the largest known. The answer involves a technique of exquisite ingenuity, made possible by the physics of light and the geometry of very long baselines. Interferometry. When two telescopes observe the same source of light simultaneously, the waves of light arriving at each telescope have traveled slightly different distances, because the telescopes are in different positions. These two sets of waves can be combined, and the pattern of their interference, the way they add together and cancel each other, contains information about the angular size of the source. The farther apart the telescopes, the finer the detail that can be resolved. One of the key instruments used to measure UY Scuti is the amber instrument on the Very Large Telescope Array in Chile. The Very Large Telescope, operated by the European Southern Observatory, consists of 4 large unit telescopes, each with an 8.2-meter primary mirror, working in combination with several smaller auxiliary telescopes. Amber, the astronomical multibeam combiner, takes the light from 3 of these telescopes simultaneously and combines it to extract angular information with extraordinary precision. The resolution achieved by interferometry depends on the wavelength of light being used and the baseline. The distance between the telescopes. Amber operates in the near-infrared, at wavelengths where the emission from cool red giant stars is strongest, with baselines of up to approximately 130 meters between the telescopes. It can resolve angular features as small as a few milliarcsecons, a unit so tiny that it represents the angle subtended by a human hair viewed from about 10 kilometers away. It is with this kind of precision that the angular diameter of UY Scuti has been measured. From the angular diameter and a knowledge of the distance to the star, itself derived from parallax measurements and distance models, astronomers calculate the physical radius, the uncertainties, as always with measurements made across such distances and through such obscuring dust, remain significant. Different studies have produced different numbers. The range of 900 to 1,700 solar radii reflects the genuine difficulty of the measurement, not a failure of the technique. But consider what we have done. We have built instruments of glass and metal and software. We have placed them on a mountain in Chile, pointed them at a faint red point in the constellation Scutum, and asked them to measure its width across 6,000 light-years of space, through dust and gas and the interference of the galactic plane, to a precision finer than any human sense could achieve. And we have an answer, imperfect, uncertain, but real. The universe allows itself to be measured. It does not always make it easy, but it allows it. Running word count, narration only across parts 1 and 2 approximately 12,400 words. Estimated runtime at 150 WPM, approximately 83 minutes. With deliberate pacing, musical interludes, and production breathing room. This section brings a cumulative runtime to approximately 120 to 140 minutes. When starlight reaches us, it carries a message, not a message in words or symbols, not the kind of message you read and set aside, a message written in the language of atoms, in the precise wavelengths of light that each element in the universe absorbs and emits when electrons move between their energy levels. A language so specific, so fingerprint precise, that if you know how to read it, you can determine the composition of a star's atmosphere from a distance of thousands of light years. This is spectroscopy, the art and science of dispersing light into its component wavelengths and reading what is written there. When astronomers turn a spectrograph toward UY Scuti, the resulting spectrum is rich and complex. The broad sweep of a red star's thermal emission, the warm, full light of a surface burning at 3,550 Kelvin, is overlaid with hundreds of narrow dark lines, called absorption lines. Each one is a fingerprint of a specific atom or molecule in the star's outer atmosphere. Iron, titanium, vanadium, calcium, water vapor, titanium oxide, which formed abundantly in the cool atmospheres of M-type stars and created a series of broad, distinctive absorption bands that give their spectra a characteristic banded appearance. From the positions of these lines, astronomers can measure the radial velocity of the star, how fast it is moving toward or away from us, through the Doppler shift of the wavelengths. A star moving away stretches its light toward longer, redder wavelengths. A star moving toward us compresses it toward shorter, bluer wavelengths. The shift is tiny. It is measured in fractions of a nanometer, but the precision of modern spectrographs is sufficient to detect it, and from it, to map the dynamics of UY Scuti's atmosphere, the swirling, expanding, contracting outer layers of this enormous star. There's a complication, as there so often is when observing to the crowded inner galaxy. The interstellar dust that lies between us and UY Scuti does not simply dim the star's light. It also selectively absorbs and scatters certain wavelengths, distorting the spectrum in ways that are difficult to fully correct for. Some of the absorption lines in UY Scuti's spectrum are not from the star at all. They are from the dust clouds between us and it imprinted on the light during its long journey. Separating the star's own atmospheric signature from the contamination of the intervening medium requires careful modeling and comparison with nearby stars observed through similar lines of sight. It is painstaking work. It is slow. It sometimes yields more uncertainty than certainty. But each spectrum is a letter from UY Scuti, a slow dispatch, 6,000 years in transit, carrying the chemical autobiography of one of the largest known stars in the universe. We read it as carefully as we can, with the best instruments we have, and we write down what it says. There's a kind of scientific patience that is almost indistinguishable from meditation. Photometry, the careful, systematic measurement of the brightness of a star over time, requires that astronomers return to the same patch of sky again and again over months and years, and sometimes decades, and measure how much light is arriving. Not just once, not just twice, hundreds of times, thousands of times, building a record point by careful point of how a star's brightness changes over time. For UY Scuti, this record is the light curve, the graph of brightness against time that reveals the pulsational heartbeat of a star. The light curve of UY Scuti shows a wave pattern, not a perfect, smooth sinusoid, but an irregular undulation, sometimes steeper on one side, sometimes shallower, sometimes punctuated by smaller subsidiary variations superimposed on the main cycle. This is what makes it semi-regular. The dominant period of approximately 740 days is clear, but the details change from cycle to cycle, and shorter period variations are present that suggest multiple pulsation modes operating simultaneously within the star's enormous atmosphere. What does this tell us? The shape of a light curve is a window into the interior of a star. By comparing the observed variations in brightness to the predictions of stellar structure models, mathematical descriptions of how pressure, temperature, density, and energy transport vary through the interior, astronomers can constrain the physical properties of the star itself. How much energy is generated in the core? how it moves through the layers above, where the pulsations are driven, and how they propagate outward. For a star like UY Scuti, this modeling is extraordinarily difficult. The interior physics of a cool red hypergiant, the complex interplay of radiation pressure, convection in enormously deep convective zones, and the complicated opacity of a cool atmosphere, is at the frontier of what stellar physics can describe. The models are imperfect. The uncertainties are large. But the light curve itself is simply there. Measured, recorded, the star's brightness, tracked across years by observers at many different observatories, assembled into a record that will outlast any single astronomer's career. There is something deeply grounding about that continuity. The records of variable star brightness go back over a century in some cases, kept by amateur and professional astronomers alike, accumulated with the same quiet diligence the Bonner Durchmusterung surveyors brought to their work in 1860. The star changes. The humans watch. They write it down. The record grows. Slowly, steadily, fact by measured fact. A star does not have a surface the way the Earth has a surface. When you stand on the Earth and look down, there is a clear boundary, solid ground, a line where the atmosphere ends and the rock begins. You could, in principle, draw a line around the Earth and say, everything below this line is planet. Everything above it is not. Stars have no such line. A star is a sphere of plasma, a gas in which electrons have been stripped from their atomic nuclei by the fierce heat of the interior. At the center, the plasma is extraordinarily dense and hot. Moving outward from the center, it becomes progressively less dense and cooler. The transition from interior to atmosphere is gradual. There is no moment at which you cross from inside to outside. There is only an extended zone over which the density drops and the opacity to radiation changes. So, how do you define the size of a star? Astronomers use the concept of the photosphere, the layer from which light can most effectively escape into space. More precisely, they use the Rosseland mean optical depth as the criterion. When the optical depth equals 2/3, meaning that only a fraction of the radiation at that depth manages to escape directly outward, while the rest is scattered or absorbed. That depth is defined as the stellar surface. The radius of that optical depth is called the Rosseland radius. It is a definition born of practicality rather than physics. There is nothing physically special about optical depth 2/3 compared to optical depth 1/2 or optical depth 1. But it is a consistent, reproducible criterion that allows astronomers to compare the sizes of different stars on the same basis. When we say that UY Scuti has a radius of 900 to 1,700 solar radii, we are using this Rosseland radius definition. When the same definition is applied to the Sun, the resulting value is the solar radius used as a comparison unit. And when it is applied to other red supergiants, H Scorpii, KW Sagittarii, V354 Cephei, the same protocol ensures a comparison is fair. AH Scorpii, KW Sagittarii. These are the stars that were measured alongside UY Scuti in the key 2012 study, each one enormous, each one a red hypergiant in the late stages of its evolution, each one measured by the same instrument, with the same technique, under the same definitional framework, so that the resulting radii can be meaningfully compared. It is one of the quieter kinds of scientific rigor, the careful agreement on definitions before measurement begins. It is the kind of thing that seems obvious in retrospect and requires considerable thought and consensus in the doing. The Rosalind radius of UY Scuti, a number defined with care, measured with precision, and still surrounded by genuine uncertainty, which is perhaps the most honest description of any measurement made across 6,000 years of space. In 2013, the European Space Agency launched the Gaia spacecraft. Gaia is one of the most ambitious astrometry missions ever conceived. Its purpose is elegant and profound: to measure positions, distances, and motions of over 1 billion stars in the Milky Way with unprecedented precision. It does this through parallax, the same geometric principle that lets our two eyes perceive depth. By observing the same star from opposite sides of the Earth's orbit around the Sun at 6-month intervals, and measuring the tiny apparent shift in the star's position against the background of distant galaxies, the distance to the star can be calculated from pure geometry. For nearby stars, Gaia's parallax measurements are extraordinarily precise. For stars like Alpha Centauri, just 4 light-years away, the parallax angle is large enough to measure with very high confidence, and the resulting distance is known to within a tiny fraction of a percent. But as stars become more distant, the parallax angle shrinks. At 5,900 light-years, the angle is extremely small, approximately half a milliarc second, and the measurement becomes correspondingly difficult. Small errors in the measurement of such a tiny angle produce large uncertainties in the derived distance. When early Gaia data suggested a distance to UY Scuti of approximately 4,900 light-years, somewhat closer than the previously assumed 5,900, the implications for the star's radius were significant. If the star is closer than thought, and the angular diameter as measured by interferometry stays the same, then the physical radius must be smaller. The early Gaia figures produced estimates of the radius as low as 755 solar radii. 755 solar radii. Still enormous. Still one of the largest known stars, but substantially smaller than the earlier estimates, and no longer so clearly the largest of all. However, the early Gaia data for UY Scuti came with a cautionary note that the astronomical community took seriously high astrometric noise. In Gaia's data processing, a measure called the renormalized unit weight error, the statistical indicator of how well the data fits a simple stellar motion model, was elevated for UY Scuti. This elevated noise suggested that the distance measurement was unreliable, contaminated perhaps by the star's own variability, by the crowded field of the galactic disk, or by the scattered light from the surrounding dust envelope. Later refinements to the Gaia data and subsequent data releases with improved processing pipelines, converge back toward the longer distance estimate of approximately 5,900 light-years. The dispute has not been fully resolved. The true distance to UY Scuti, and therefore its true radius, remains an open question that subsequent and future astrometric data may eventually settle. Science moves in this way, not in sudden revelations, but in slow convergences, each instrument adding its piece, each revision refining what came before. A number is proposed. A better measurement challenges it. A better measurement still refines the challenge. And gradually, over years and decades, the uncertainty narrows. UY Scuti waits, as it always has, with complete indifference to the question. Every measurement carries uncertainty. This is not a flaw of measurement. It is the nature of knowledge itself. The honest acknowledgement that our instruments are finite, our models are approximations, and the universe does not owe us simple answers. For UY Scuti, the uncertainties are particularly deep, and they stack. The first layer of uncertainty is distance. As we have seen, the distance to UY Scuti is known imprecisely. Different methods, different data sets, different modeling assumptions produce distances that range from roughly 4,900 to 6,000 light-years. This is a range of approximately 20%. And because the physical radius of the star is calculated by multiplying the angular radius by the distance, a 20% uncertainty in distance propagates directly into a 20% uncertainty in radius. The second layer is dust extinction. The interstellar dust between us and UY Scuti absorbs and scatters the star's light, dimming it and reddening it, to determine the star's true brightness, and from that, to model its luminosity and temperature, astronomers must subtract this dust effect. But the amount of dust is not known precisely. It is estimated from models of dust distribution in the galactic disk, combined with measurements of the reddening of the star spectrum. These models are imperfect, and different assumptions about the dust produce different corrected luminosities. The third layer is the definition of radius itself. As we discussed with the Rosalind radius, the boundary of a star is not a sharp line but a defined convention. Different conventions give slightly different answers. The fourth layer is the pulsation. Because UY Scuti changes in size over its 740-day cycle, a measurement made at one phase of the pulsation will give a different radius than a measurement made at another. The timing of observation matters, and comparing measurements made at different times requires care. All of these uncertainties compound each other. When you add them together, the resulting range of plausible radii spans from approximately 900 to over 1,700 solar radii. Not because astronomers are careless. Quite the opposite. The range reflects the genuine difficulty of the measurement, honestly acknowledged. There is something almost restful about this uncertainty. In the quiet of a late night, we do not need to know the exact size of UY Scuti for it to be magnificent, whether the radius is 900 solar radii or 1,700. The star is one of the most extreme objects in the observable universe. The uncertainty is in the precise number, not in the wonder. The wonder is intact. The number will improve over time. Future instruments, future data releases, future measurements from space observatories operating in wavelengths that cut through the dust more cleanly. These will narrow the range. But the star will remain enormous, and the night will remain dark. And the question will have been worth asking at whatever answer it eventually arrives. No single instrument tells the whole story. This is a principle that runs through all of science. The recognition that each method of observation has its own blind spots, its own systematic biases, its own particular way of being wrong. The only remedy is to look at the same thing in multiple ways, with multiple instruments, from multiple vantage points, and to compare what each one says. Where they agree, confidence increases. Where they disagree, the disagreement is itself informative, a clue about the limitations of one or both methods. For UY Scuti, this multi-instrument philosophy has been applied with particular care. The Very Large Telescope, with its amber interferometric instrument, provides the most direct measure of angular size, the actual angular width of the star's disk on the sky. This measurement is extraordinarily precise for what it measures, but it requires a distant assumption to convert angular size into physical size, and it is best suited to near-infrared wavelengths where the star's emission peaks. Gaia, the European astrometry satellite, provides the distance measurement through parallax. As we have seen, this measurement is challenging for UY Scuti, given the distances involved and the contaminating noise from the galactic environment. Gaia's early data, Release 3, the third major release of refined astrometric data, improved the distance estimate substantially, though uncertainties remain. Adaptive optics systems on large ground-based telescopes address a different problem: the blurring of starlight by Earth's turbulent atmosphere. When light from a distant star passes through the atmosphere, it is continuously refracted and scattered by temperature fluctuations, creating the familiar twinkling of stars and, more problematically for precision measurement, a smearing of the star's image that limits resolution. Adaptive optic systems combat this by measuring the atmospheric distortion in real time, using a bright reference star or an artificial laser guide star, and applying compensating corrections to a deformable mirror that flexes thousands of times per second to undo the atmospheric turbulence. With adaptive optics, the effective resolution of a ground-based telescope approaches the theoretical limit set by the telescope's aperture rather than by atmospheric conditions. For UY Scuti, this means the ability to more precisely determine whether the disk of the star is truly circular, as a spherical star would appear, or whether it shows evidence of asymmetries, of material being shed preferentially in certain directions, of the complex surface structures that some red hypergiants are known to possess. The combination of interferometry for angular size, Gaia for distance, and adaptive optics for structural detail creates a picture more robust than any single method alone. Each data source constrains the others. When all three converge on consistent answers, confidence in the result is substantially higher than when relying on any one. 3 instruments, 3 methods, 1 star, and gradually, patiently, a clearer picture forming. This is how knowledge grows, not in flashes, but in slow accumulation, each measurement adding a small brick to a wall that will outlast the builders. Behind every number in astronomy, there is a model, not a physical model, not something you can hold or touch, a mathematical model, a set of equations that describe how a star works, how energy moves through it, how its outer atmosphere absorbs and emits radiation, how it evolves over millions of years from a young hot star to an aging cool giant. These equations encode the physics of stars, the nuclear reactions in the core, the radiation transport to the layers above, the thermodynamics of an atmosphere that is simultaneously a gas, a fluid, and a radiating surface. For UY Scuti, astronomers use several families of modeling codes, each one designed for a specific piece of problem. Atlas and Phoenix are atmospheric codes, programs that simulate the properties of a stellar atmosphere, computing the predicted spectrum of light that should emerge from a stellar surface with specified temperature, gravity, and chemical composition. The principle is straightforward in outline. Given a model atmosphere, calculate what the emerging spectrum should look like, then compare it to the observed spectrum. Adjust the model parameters until the predicted and observed spectrum match. The parameters that produce the best match, temperature, surface gravity, chemical abundances, are your best estimates of the star's actual properties. For cool stars like UY Scuti, this modeling is technically demanding. The atmosphere of a cool M-type star contains a complex mixture of atoms and molecules, titanium oxide, vanadium oxide, water vapor, carbon monoxide, each with thousands of spectral lines that must be accounted for in the calculation. The Phoenix code in particular has been developed over decades specifically for this challenge, and it contained atomic and molecular line databases of extraordinary detail. MESA, the modules for experiments in stellar astrophysics, addresses a different aspect of the problem: the interior structure and evolutionary history of the star. MESA integrates the equations of stellar structure forward in time, beginning from an initial configuration of gas and evolving it through successive phases of nuclear burning: hydrogen to helium, helium to carbon and oxygen, carbon and neon and oxygen and silicon, tracking how the star's radius, luminosity, and surface temperature change over millions of years. By identifying which evolutionary tracks in the MESA models pass through the region of the Hertzsprung-Russell diagram occupied by UY Scuti, astronomers constrain the star's initial mass and its current evolutionary state. These codes are not perfect. They are approximations of physics that is, in the most demanding cases, at the edge of what we can calculate. The deep convective zones of red supergiants, where vast bubbles of hot plasma rise and fall over timescales of months, cannot be fully simulated. The treatment of mass loss, the stellar winds that are stripping material from UY Scuti's outer layers, involves parameterizations that are calibrated from observations, but cannot be derived from first principles alone. But the models improve year by year as computing power grows and as physical understanding deepens. And each comparison between a model prediction and an observation of UY Scuti is a small act of understanding, a narrowing of the gap between what we have imagined about stars and what they actually are. Science rarely delivers its findings in single, clean moment of revelation. The story of UY Scuti's modern measurement is a story of exactly this, of initial excitement, of subsequent revision, of the slow refinement that characterizes knowledge honestly pursued. When a 2012 study, using amber interferometry on the Very Large Telescope, published its measurements of UY Scuti alongside H Scorpii and KW Sagittarii, the result was striking. The angular sizes measured, combined with the distance estimates available at the time, placed UY Scuti's radius at approximately 1,700 solar radii, possibly higher. The announcement that the star might be the largest known attracted considerable attention, both within the astronomical community and in popular science communication. But science does not stop at the first answer. The Gaia mission, as we have discussed, subsequently provided new distance data that, in its initial form, suggested a shorter distance and therefore a smaller radius. Later refinements adjusted this back toward the original estimate, but with enough remaining uncertainty that the picture became more complicated than the initial clean announcement had suggested. Revised analyses of the original VLT data, incorporating improved atmospheric modeling and more careful treatment of the dust extinction, also produced somewhat different radius estimates than the initial publication. The number was revised downward in some analyses, though never to a value that removed UY Scuti from the ranks of the most extreme stars known. And this is exactly how it should be. The initial measurement was not wrong. It was a measurement honestly made with the instruments and knowledge available at the time. The subsequent revisions were not corrections of errors. They were refinements, the natural and expected process by which a first approximation is succeeded by a better one. Each revision brought the community closer to the true value, whatever that value eventually turns out to be. What the entire story of UY Scuti's measurement illustrates is something important about extreme objects at the boundaries of knowledge. When you are measuring the very largest, the very most luminous, the very most extreme examples of any class of object, the measurement is always hardest. The extreme cases are where the models are most stressed, where the instruments are pushed closest to their limits, where the dust is thickest and the distances are greatest. And that is precisely why they are worth measuring. Because the extreme cases are where physics is most tested, where our understanding either holds or breaks, where we learn what stars can actually be. UY Scuti, regardless of where its radius eventually settles, has taught us something about the boundaries of the possible. That is not a small thing. In the high, dry desert of the Atacama Plateau in northern Chile, an altitude of over 2,600 meters above sea level, there's a mountaintop called Cerro Paranal. The air above Cerro Paranal is among the clearest and most stable on Earth. Fewer than 10 days per year see observing conditions compromised by cloud or humidity. The seeing, the astronomical measure of atmospheric turbulence, is exceptionally good for most of the year, and the remoteness of the site, far from the light pollution of cities, means that the night sky above it is as dark as anywhere accessible to major infrastructure. It is here that the European Southern Observatory built a very large telescope. For unit telescopes, each one an 8.2-meter mirror housed in a dome the size of a small building, working in concert with an array of auxiliary instruments and the amber interferometric combiner that brought UY Scuti's angular size within the reach of measurement. The study that emerged from observations made with this instrument, published in 2012, targeted 3 red hypergiant stars simultaneously: UY Scuti, AH Scorpii, and KW Sagittarii. All 3 are members of the same rare class of extreme evolved stars. All 3 are located in the direction of the galactic center in the dust-rich inner Milky Way. And all 3, when their angular sizes were combined with available distance estimates, emerged as candidates for the title of the largest known stellar radius: AH Scorpii, KW Sagittarii, names that perhaps only a specialist in stellar evolution might recognize. But in the context of this measurement, they are companions to UY Scuti, stars that submitted to the same instrument on the same nights, measure with the same protocol, their angular disks resolved by the combining of light from 3 of Paranel's great telescopes. The amber instrument works in the near-infrared at wavelengths of 1 to 2.5 microns, where the emission from cool red stars is strongest and where the angular resolution achievable through interferometry is highest relative to the measured signal. The baselines between the telescopes, up to 130 meters, provided the spatial frequency coverage needed to fit a uniform disk model to the visibility data, extracting an angular diameter that could then be translated into a physical radius. The result in 2012 was the angular diameter of UY Scuti measured as approximately 5.4 plus, or minus 0.4 milliarc seconds. A number so small that it takes more than a moment to feel its meaning. 5 milliarc seconds. 1/5,000,000th of a degree. The angle subtended by a golf ball, observed from a distance of about 60 kilometers. And from that impossibly tiny angle, combined with an assumed distance, emerged a claim: the largest known star. In the high, dry dark above Paranel, the light of UY Scuti, ancient when it left the star, ancient still when it crossed the threshold of the telescope's primary mirror, was caught, combined, and made to yield its secret. For a brief and celebrated period following the 2012 paper, UY Scuti wore a particular distinction: the largest known star in the Milky Way. That title, in the context of popular science communication, carries a certain kind of wonder. It is a kind of superlative that people can hold and share, that conveys something of the universe's capacity for extremity, that turns an obscure designation in a 19th century catalog into a name that circulates in documentaries and science articles and late-night conversations about the size of things. Before UY Scuti's 2012 measurements drew wide attention, the title of largest known star had been held at different points by different candidates. Betelgeuse, the red giant marking the left shoulder of Orion, one of the most recognizable stars in the night sky, visible in winter from most of the inhabited Earth. A star so large that it had been among the first resolved as a disk rather than a point by early interferometric measurements. Betelgeuse has a radius of approximately 700 to 1,000 solar radii, depending on the measurement method and the phase of its pulsation cycle. Its own measurements carry significant uncertainty, and it is notably variable, famously so in late 2019 and early 2020, when it dimmed substantially enough that astronomers began discussing whether it might be approaching a supernova, before brightening again and revealing the dimming to be caused by a dust ejection event rather than imminent death. UY Canis Majoris, the great star, the big dog constellation, discussed earlier in our slow tour, with approximately 1,400 solar radii and its own rich circumstellar nebula of ejected material. UY Canis Majoris was considered a leading candidate for the largest known star for a considerable period, and the comparison between it and UY Scuti was the central claim of several popular science treatments of the subject. An ML Cygni, roughly 1,650 solar radii, in the constellation of the Swan, also enormous, also variable, also surrounded by the complex circumstellar chemistry of an aging hypergiant. And then UY Scuti post 2012, briefly occupying the summit. The name spread through the popular astronomy community. It became the answer to a certain kind of question. It became the example that science communicators reach for when they wanted to illustrate the sheer scale of what the universe contains. The record has since become more contested, as better data on Stephenson 2 to 18 and revised estimates for UY Scuti itself have blurred the rankings. The leaderboard of the largest known stars is not fixed. It shifts with every new measurement, every refined distance, every improved interferometric image. But UY Scuti remains in the conversation. It will always remain in the conversation. A star discovered in 1860, cataloged as a number barely visible from Earth, burning in the quiet heart of the Milky Way, and one of the most extreme objects in the observable universe. The record may change. The star does not. Running word count, narration only across parts 1, 2, and 3, approximately 18,500 words. Estimated runtime at 150 WPM, approximately 123 minutes. With deliberate pacing, musical interludes, and breathing room, the cumulative runtime for parts 1 to 3 comfortably exceeds 2.5 hours. In 1860, a man in Bonn wrote down a number. He wrote it in ink in a ledger by the light of a lamp. He recorded the position of a faint reddish star in the constellation Scutum, its coordinates in the sky, its approximate brightness, the zone it belonged to. The entry was one of 300,000 entries in a comprehensive survey of the visible sky. It took perhaps 30 seconds to write. The pen moved on. The number recorded was a brightness, an estimate made by eye of how bright the star appeared relative to its neighbors. This was the state of the art. The human eye, adapted over millions of years of evolution for life on a dark savanna, is a genuinely sensitive instrument for detecting the presence of faint light, but it cannot measure brightness precisely. It cannot determine temperature. It cannot resolve the angular diameter of a distant star. It can only say, "This is here, and it is approximately this bright." 152 years passed. In 2012, on a mountain in the Atacama Desert, 3 enormous mirrors gathered the same starlight. Photons that had left UY Scuti 5,900 years earlier, during the Bronze Age of the ancient world, before any of the civilizations that built the instruments to receive them existed. The mirrors reflected this light through a system of optical fibers and beam combiners, producing interference patterns on a detector cooled to cryogenic temperatures to minimize thermal noise. From those interference patterns, software extracted an angular diameter. From the angular diameter and a distance measurement, a physical radius was calculated. From spectroscopic observations taken alongside the interferometry, a temperature was derived. From the temperature and radius, a luminosity, 124,000 to 340,000 times the luminosity of the sun, more than 100,000 solar luminosities, a number that would have been meaningless to the astronomer in Bonn in 1860, not because he lacked the intelligence to understand it, but because the concept of luminosity in those terms and the instruments to measure it did not yet exist. Between 1860 and 2012 lies a century and a half of accumulated ingenuity. Photographic plates replacing the human eye, spectrographs splitting light into its component colors, photoelectric detectors replacing photographic plates, CCD sensors replacing those, interferometers combining the light of multiple large mirrors, satellites above the atmosphere, software solving equations that describe the interiors of stars. Each generation of instrument asks better questions of the star, and the star, patient, enormous, burning in the dark, answered with whatever information it had always been sending. The star did not change between 1860 and 2012. Only our capacity to listen did. That is the story of technology, not replacement of what came before, but the slow growth of our ability to hear what the universe has always been saying. A star's life is a journey across a diagram. The Hertzsprung-Russell diagram that we have visited several times tonight is not just a static map of where stars currently are. It is a record of journeys. Every point on the diagram is a moment in a stellar life, a snapshot of what a star looks like at one particular phase of its evolution. Over millions of years, stars move across the diagram as their internal structure changes, tracing paths that theorists can model and observers can sometimes catch in progress. UY Scuti's journey has been long and complex, and it is not yet finished. The star began its life on the main sequence, as all stars do, with a mass of approximately 25 to 40 solar masses. It would have been a brilliant hot blue star in its youth, an O-type or early B-type star blazing at temperatures of perhaps 30,000 Kelvin or more, pouring out ultraviolet radiation, driving powerful stellar winds even then, living in the intense, brief manner of all massive stars. After a few million years of main sequence hydrogen burning, the core exhausted hydrogen and the star began to evolve. It moved rightward on the Hertzsprung-Russell diagram, cooling at its surface, expanding in its outer layers, passing through the supergiant phase and eventually arriving at its current position as a red hypergiant, fusing helium in its core while hydrogen burning continues in the shell around it. The future is uncertain in its details, but the broad outlines are constrained by stellar physics. As UY Scuti continues to evolve, it will likely move back toward higher temperatures, back leftward across the diagram. Some massive stars in this phase transition through a yellow hypergiant phase, a brief and highly unstable period during which the star pulsates violently, shedding mass rapidly in eruptions. Some may pass through a phase resembling a luminous blue variable, a category of massive star known for dramatic, sudden increases in brightness and enormous mass ejection events. Eventually, if enough of the hydrogen envelope is lost, the star may arrive at the Wolf-Rayet phase, a category of stars so hot and so stripped of its outer layers that its spectrum is dominated not by absorption lines, but by broad emission lines, the signature of a star whose core is nearly exposed to space. Each of these phases is a waypoint in a journey toward an inevitable end. The journey across the diagram takes, in total, only a few million years. On a cosmic scale, this is an extraordinarily brief transit. The red hypergiant phase, the phase UY Scuti currently occupies, may last only tens of thousands of years. A geological instant, asleep almost by the standards of stellar time. And then the end, but slowly, always in this story, slowly, at the center of UY Scuti, right now, something is happening that has been happening for millions of years. Nuclear fusion. In the core, the dense, fiercely hot inner region where temperatures are measured in hundreds of millions of degrees and pressures are beyond anything earthly experience can approximate. Atomic nuclei are colliding and merging. Helium nuclei, the ash of the hydrogen burning that characterized the earlier phases of the star's life, are now themselves being fused into carbon and oxygen. The energy released by this process, the energy of mass being converted into radiation, according to the most famous equation in physics, is what holds a star up against the enormous inward pull of its own gravity. But fusion cannot continue indefinitely through the heavier elements. As the helium in the core is consumed, it will be replaced by a core of carbon and oxygen. When the carbon ignites, it will burn to neon and magnesium, neon to oxygen, oxygen to silicon, silicon to iron, iron is where fusion ends. Unlike the lighter elements, which release energy when fused into heavier ones, iron is the most tightly bound of all nuclei. Fusing iron does not release energy. It absorbs it. When the core of a massive star accumulates enough iron, fusion ceases to support it. There is no more energy to be extracted. And when fusion stops, gravity wins. The core collapses. In less than a second, a duration almost impossible to reconcile with the millions of years that preceded it, the iron core, with a mass greater than the Sun, collapses inward from roughly the size of Earth to roughly the size of the city, a sphere 20 kilometers across. The collapse is so rapid and so violent that the infalling material bounces off the newly formed ultradense remnant, and an enormous shock wave explodes outward through the star. This is the core collapse supernova. For a brief period, days to weeks, the explosion is brighter than the entire galaxy that contains it. Billions of suns worth of light, pouring outward from a single point, UY Scuti supernova. When it eventually comes, may be visible from Earth even in daylight, despite a distance of 5,900 light years. It will appear suddenly as a new and brilliant star in the constellation Scutum, a star where none was visible before, slowly brightening, and then, over weeks and months, slowly fading. What remains afterward depends on the details of collapse. If the core remnant has enough mass, it will continue collapsing past the neutron star phase, past even the extraordinary density of neutron matter, and become something from which not even light can escape, a black hole. If the collapse leaves a neutron star, a sphere of matter so dense that a teaspoon would weigh 1 billion tons, it may spin rapidly and emit pulses of radio waves. A pulsar, the most precise natural clock in the universe. UY Scuti does not know this yet. Its iron core is not formed. Its fusion continues. It burns and expands and pulsates and sheds its outer layers into the growing cloud around it. And by any measured time that a human life can contain, it will continue to do so. The end is coming. In stellar time, it is close. But even close in stellar time is a very long way from now. Nothing in the universe is wasted. This is not a philosophical statement. It is a physical one. The material that makes up stars and planets and moons and the thin wisps of gas between galaxies is the same material that has always been here. Since the first few minutes of the universe, when protons and neutrons and electrons emerge from primordial plasma, it cannot be created or destroyed. It can only change form. And UY Scuti, in its dying, will change form in one of the most generous ways the universe permits. Even now, while it lives, UY Scuti is giving. The stellar wind streaming outward from its loosely held atmosphere, carrying gas and dust at speeds of hundreds of kilometers per second, enriched with the products of nuclear burning in the stellar interior, are seeding the interstellar medium with material, carbon, oxygen, heavier elements formed in the deep nuclear fires of the core, dust grains condensing in the cooling outflow, tiny seeds that may one day become incorporated into the disk of gas around a forming star and eventually aggregate into a rocky planet. The circumstellar envelope that surrounds UY Scuti, extending 400 astronomical units in every direction, is a reservoir of this material. As it expands and eventually merges with the broader interstellar medium, it will enrich the gas clouds for which the next generation of stars forms. The stars that form from that enriched material will contain more heavy elements than the ones that formed before UY Scuti contributed its substance to the mix. Their planets, if they have planets, will be made of richer material, And then when the supernova comes, the core collapse, the shock wave, the brief blaze of impossible brightness, the remainder of UY Scuti's mass will be ejected violently into space. The heavier elements formed in the star's core over millions of years of fusion, iron, nickel, and in the extreme energies of the explosion itself, elements heavier than iron, copper, zinc, gold, silver, uranium, will be scattered into the surrounding medium. These elements are now or will become part of everything. The iron in your blood was made in a star, not necessarily UY Scuti. That star has not yet died, but in a star of its kind, somewhere in the galaxy, billions of years ago, a core collapse supernova scattered that iron into the interstellar medium. It drifted. It condensed into the cloud that formed our solar system. It became the Earth. It became life. It became the hemoglobin in your blood that carries oxygen to your cells right now as you breathe slowly in the dark. UY Scuti is doing, on a different time scale, what has already been done for you. It is becoming the future. Every measurement made of UY Scuti has left something behind, not just a result, the number, the angular diameter, the luminosity, the classification, but a method, a technique refined, a model improved, a question more precisely formulated for the next generation of observers to answer. The Bonner-Durchmusterung of 1860, which gave us BD 12°5055, was itself an achievement that shaped the practice of stellar astronomy for a century. The systematic survey of the sky, zone by zone, star by star, position and brightness recorded with the care of people who understood that someone would one day need this information, establish a template for how catalogs are made. Every subsequent star catalog, including the Hipparcos catalog of the 1990s and the Gaia catalog of the 2010s and 2020s, is in some sense the descendant of the Bonner-Durchmusterung. The variable star studies of the late 19th and early 20th centuries that reclassified BD 12°5055 as UY Scuti contributed to the development of the variable star classification system that still orders our understanding of stellar variability today. The spectroscopic observations that characterize UY Scuti as an M-type hypergiant contributed to the population studies of red supergiants in the inner galaxy, studies that map the distribution and properties of the most massive stars in the Milky Way and provide constraints on models of galactic chemical evolution. The 2012 Amber Interferometry campaign that measured UY Scuti alongside H. Scorpii and KW Sagittarii was a landmark study in the interferometric measurement of stellar angular diameters. The techniques developed and validated in that campaign have been applied to dozens of other stars since, expanding the catalog of stars with directly measured angular sizes. The systematic uncertainties identified in that work, the difficulties of measuring cool red giants whose atmospheres are complex and whose boundaries are diffuse, have driven improvements in stellar atmosphere models, and the Gaia parallax complications surrounding UY Scuti's distance measurement have contributed to ongoing work on improving astrometric measurements in crowded, dusty fields, work that will benefit the study of many thousands of stars, not just this one. UY Scuti, in this sense, is not just a star. It is a test case, a calibration source, a challenge that has pushed the boundaries of what our instruments can do and our models can predict. The star does not know it has been useful. It simply burns. But the light it sends across 5,900 light years of space carries, encoded within it, questions that astronomers have spent a century and a half learning to ask correctly. From a ledger entry in Bonn to an interferometric measurement in Chile to a satellite cataloging 1 billion stars from space. The thread of human curiosity about this single red point has stretched unbroken across generations, each one passing the question forward, slightly better answered, to the next. The story is not finished. This is perhaps the most quietly reassuring fact of all, that after everything we have learned about UY Scuti, its discovery in 1860, its variable star classification, its position in the inner galaxy, its angular diameter measured by interferometry, its luminosity 100,000 times the sun's, its pulsation cycle of 740 days, its circumstellar envelope of gas and dust, its eventual fate as a core-collapsed supernova. After all of it, there is still more to know. The discrepancies between different measurements of UY Scuti's size remain unresolved. The Gaia parallax and the amber interferometry do not yet fully agree. The Rosalind radius derived from atmosphere models with different assumptions spans a range of 900 to 1,700 solar radii. The question of whether UY Scuti is the largest star in the Milky Way, or whether NML Cygni or Stephenson 2 to 18 might surpass it, cannot be definitively answered with current data. Future missions will address these questions. The next generation of optical and infrared telescopes, instruments with larger mirrors, better adaptive optics, and longer interferometric baselines than anything currently in operation, will measure angular diameters with greater precision. The extremely large telescope under construction in Chile's Atacama Desert will have a primary mirror 39 meters across, dwarfing the 8.2-meter mirrors of the VLT. With its adaptive optic systems, it will achieve resolution never before possible from the ground. Future Gaia data releases will continue to refine parallax measurements throughout the galaxy, with better treatment of the systematic effects that complicated early measurements of stars in crowded, dusty fields like the one that surrounds UY Scuti. New spectroscopic surveys, with spectrographs attached to large telescopes covering wide areas of sky simultaneously, will provide more detailed chemical and dynamical information about the population of red supergiants in the inner galaxy, giving context to UY Scuti's measured properties and allowing better statistical comparisons. And the ongoing theoretical work, the stellar atmosphere models, the evolution codes, the simulations of mass loss and circumstellar envelope structure, will continue to improve, driven in part by the challenge of explaining what observers have found. UY Scuti, discovered in 1860 and intensively studied since 2012, will be more precisely understood in 2030, and better still in 2040, and better again after that, Each generation of astronomers will know it a little more clearly than the one before. This is what science is: an ongoing conversation between human curiosity and the universe's willingness to be known, not a destination, a direction, a slow and patient and endlessly rewarding movement toward understanding. The star burns, the instruments improve, the questions sharpen, and the distance between what we know and what we do not know narrows very slowly, like the long approach of dawn. You have traveled a long way tonight, from a desk in Bonn in 1860 to a mountain in Chile in 2012, to the cold outer reaches of a dust cloud 400 astronomical units wide, to the interior of a star where iron is not yet formed but will one day, slowly and inevitably, end the burning. You have visited a star so large that if it sat where our sun sits, you would be inside it. You have heard its light curve, the slow rise and fall of its brightness over 740 days, described as breathing, because that is what it is: a breath, an enormous, unhurried breath, measured in years, taken by something far older and larger than anything on the small, warm world where you are lying right now. Let your own breathing slow now. There is no need to remember any of this. The universe does not ask you to carry it. It is simply there, in the dark beyond your window, burning and pulsating and shedding its outer layers into slow drift of space, unconcerned with being remembered, content to simply be. UY Scuti does not know you listened tonight, but you did, and that matters in the quiet way that all acts of attention matter. You turned your mind towards something vast and distant and old, and for a little while your own worries became small beside it. The way a single lamp becomes invisible in the light of a sunrise, somewhere in the constellation Scutum, 5,900 light years away, a red star is breathing. Its outer layers are moving outward now, very slowly, almost imperceptibly, a fraction of a solar radius per day, expanding in the long, patient pulsation of something that has no reason to hurry. The light from that expansion left the star when the ancient world was young. It is still traveling. It has not reached us yet. By the time it arrives, you will have slept, and the star will still be burning, and the universe will still be old, and everything will be well. Good night.